Okay, calculations involving half-life. Remember, the half-life of a material is the amount of time it takes for a radioactive material to decay to 1/2 of its original amount. Take a look at this graph that we're showing below. It represents the amount of radiation emitted by a certain sample over time. On the y-axis, you see that we start out here at 5,000 counts per minute. That means that when we originally begin to take measurements here, probably using a Geiger counter, we're seeing that it's reading about 5,000 counts per minute at the point when we have 100% of this substance. The half-life can be calculated by taking 1/2 of that original amount, or 2,500. At that point, you'll have 50% of the material. If you extrapolate that down to the x-axis, you can see that roughly about 7 hours have gone by for this particular radioactive material. Graphs are usually a little bit rough, so it makes sense to do more than one calculation. And so you can calculate a second and a third half-life by taking 1/2 of the amount you have here, 2,500, and dividing that by 2. You'll end up with about 1,250. And at that point, you're going to have about 25% of the substance. If you divide that in half again, you will have roughly about 12.5% of the substance. And so from the graph, we could get another couple of half-lives. On average, it looks like for this substance, the half-life is roughly around 7 hours. Okay, let's take a look at another type of problem you might encounter. Suppose we're given some information about an artifact that's emitting some radiation due to carbon-14. Carbon-14 is probably the most famous type of radioactive material that people have heard of, and it's used to determine the age of old artifacts and things like that. The half-life of carbon-14 is about 5,730 years, and when a living thing, is alive or recently dead, it will emit somewhere in the range of about 15.3 counts per minute, and then when the creature, the tree, or the animal dies, it's no longer eating and it's not taking in any more carbon-14, and the amount of carbon-14 will go down after that point. So in this problem, we imagine that we're given an artifact, and we use a Geiger counter and we do some sophisticated measurements, and we find out that it's emitting somewhere in the range of about 0.96 counts per minute. And we want to figure out how old is this substance. Well, if not a lot of half-lives have gone by, you can try a simplistic method here of just simply dividing by 2. So we know when this thing was alive, it was emitting at about 15.3 counts per minute. If we divide that by 2, you get about 7.65. And the rate that we're given here is less than that, so we divide by 2 again and again and again. And finally we get down to the range that we're told that this artifact is emitting at, about 0.956 counts per minute. If you look, we've got 4 half-lives that have gone by, and each half-life is 5,730 years. So to determine the age of this artifact, we take 4 times the half-life of carbon-14, 5,730, and we find that, roughly speaking, the age of this substance would be about 23,000 years, 22,900. You want to probably pay attention to your significant digits here. For example, the 0.96 has only 2 significant digits, which means that we know the age of this thing, plus or minus probably about 1,000 years or so. It's not the most precise method, but it does give us a really good estimate of when an artifact or an animal was living. So it's kind of cool. All right, so that's kind of archaic and doesn't always work, especially if you've had about 10 half-lives or more go by. Dividing by 2 gets really tedious. So there is an equation that you can use to do this as well. So we'll take a look at that right now. So I'm not going to get into where this equation comes from, and there's several different forms of this, but basically the amount of a radioactive material compared to the original amount is an exponential function. It's a decay function. It's an inverse relationship here using a natural exponent. So a lot of people won't have had the math background to understand all of that just yet. So this will probably end up being just kind of an equation that you will be given, and hopefully you'll understand how to plug some numbers into it, and later in math class you'll look at it in greater detail. But I'm going to take the log of both sides of this equation, or what's called the natural log. And when you take the log of an exponential function, that ends up being just the exponent itself. So we end up with a basic equation here that is commonly used to calculate half-life or make calculations involving half-life. In this equation, T stands for time. K represents something called the decay constant. N is the amount of this radioactive material that you have at any particular time. And the N with a little 0 below it, which is called N naught, is representing the amount of the radioactive material that you have originally or initially. And then the LN button, or the LN rather, just for this point, at this point, just kind of stands for a button on your calculator. All right, so let's take a look at how we might use this equation. It looks a little threatening, but honestly, it's not too bad. All right, so let's suppose that we are given some information about a material, and we're told that we have a substance which has a half-life of 4 days, and we need to determine the decay constant. So first of all, we would write out the equation. The natural log of n over n naught is equal to negative k times t. And in this case, we're trying to find k. So we know the time, we know a half-life at this point, but we can't solve for k until we know n and n naught. But if you remember that the half-life is the amount of time it takes for the material to decay to 1/2 of the original amount, then you can see that the ratio of n over n naught is 1/2, or 1/2. So now we have one equation with one unknown, and we're just going to do a little algebra. First, you're going to find the ln button on your calculator and press ln 0.5. You're going to get negative 0.693. And then simply just chugging away here and doing your algebra, you should find that k is 0.173. All right, so let's take a look at another type of problem. How many days will it take for the amount of radiation from this stuff, this radioactive material, to be reduced to 1/10,000th of its original level? So now that we know the decay constant, we can plug into the equation again. We know that the ratio of n to n naught is 1 to 10,000, and we know the decay constant is 0.173. Again, you're just going to press the ln button on your calculator and of 1/10,000th, and that gives you negative 9.21. Again, doing out your algebra nice and carefully, you find that the amount of time gone by here is about, roughly, again, 53 days. So, although the equation looks kind of cumbersome and a little bit threatening at first, it turns out that it's pretty easy to use once you get used to doing that. So I hope that's helpful. The half-life of substances was an amazing discovery because it could be used to determine the ages of things like dinosaur bones and ancient artifacts found in campfires and of ancient people, and really gave us a sense of determining how old things were before we had carbon-14 dating and radioactive half-life dating. We had no idea how old the Earth was, or how long ago the dinosaurs lived, or how old the moon was, for that matter. So it's an amazing thing, really, and really advanced our knowledge of the world around us.